Great.
Oh, very cool. The cat with the sunglasses. Very nice. All right, here we go. So we're back for more today. Now I have to make an announcement right up front. The scheduling for today got a little strange because one of my schools that I teach at is having our exam this afternoon. Unfortunately, it's a very long drive for me to get to that school. So today, for the only time, we're going to have to stop early so that I can get to that school on time. So rather than having a break, what I'd like to do today is simply go straight through to 11:30, and we'll stop there. And then after that, all the classes will be back to normal. Okay, so just for one day only, we'll have an hour and a half session. And then tomorrow, everything will be back to normal. And then we'll keep going with the same schedule. But this just worked out very badly for me. But I will be able, don't worry, we will not fall behind. We'll definitely get all of the work done in spite of this. So just one more time, we'll stop at 11:30, and then that will be it for today. All right, so anyway, so let's get back to Moodle and download what we have for today. Now, we're largely, no, I wouldn't say largely, but maybe halfway through chapter 3. So let's go pick that up again. Let me go open up Moodle for you. And I just want to point out a couple of things here. Let's see, where are we? First, I'll log in. Oh yeah, we got to go through this routine. Right, you never know. When hackers might want to read my purchase emails, so we have to go through this routine to get into our email accounts. And so if you look in Moodle today, you'll see that what I did was I posted the, we have not just chapter 3 here, the original copy, but if you notice, it says here chapter 3 with notes 12/20/21. That means all the handwriting that I did yesterday is included in these notes right here. So all the little sketches and drawings that I did are in here if you want to look at them again. This is just the original chapter with no writing in it. And then today, we'll do the same thing. I'll just open this up, save it with today's date, and then this way you'll have another document with whatever we write on today. So this way nothing gets lost. And this is one of those areas where, you know, compared to the classroom, you know, you can't realistically save your work from the board. So this is one of the areas where online is actually kind of helpful. Not to mention the recordings. I mean, some schools do have sophisticated equipment in each room that lets the class be recorded, but I don't think we have that, or at least not the rooms that I teach in. So, all right, let's just quickly review what we were doing yesterday. We were introducing some key concepts. We start out by describing the difference between a population and a sample. And so, as you know, a population is a collection of measurements or outcomes of interest that we are studying for whatever reason. And often it is not feasible to study the entire population. So we choose samples from that population and use those properties of that sample to draw conclusions about the underlying population. So if I'm studying the ages of all Americans in the United States, I might, as you know, a government statistical agency, decide that a sample of, let's say, 2 million is sufficient to give me enough information about the entire country. So if I've chosen the sample well, in such a way that it really reflects the overall population, whatever information I take out of that sample should be a good representation of the population. Now, of course, it's understood that there's still room for error there, and we will discuss this in more detail in later chapters. But for now, it's enough to note that for the most part, we'll be using samples of data and using those to draw conclusions about the population of interest. Okay, so then we introduced these measures of central tendency, mean, median, and mode. We went through all 3 of them, and we saw how to calculate them. The sample mean, for example, means that we're taking the elements in our sample, we add them up, we divide by the size of the sample. We also saw that there's a corresponding formula for the population mean, which is exactly the same except for the actual notation. Okay, in other words, in spite of its appearance, you're still doing the same thing. You're actually just adding up all the elements in your population and dividing by the size of the population. So in this case, while there's two separate formulas, it is the exact same procedure. We also then introduced the concept of the weighted average, which means that you have data where some of the elements are more important in some way than others, or else they repeat themselves more frequently. And in those cases, it's often easier to use a weighted average rather than trying to add up all the elements and divide by the sample size or the population size. We also saw that this is how GPAs are calculated. All right, the weights themselves are simply the number of credits that you took for each class. And so, and by the way, if every one of your classes has the same number of credits, this isn't actually necessary, because then you really could just add up these scores and divide by this number of elements you have. But since that's typically not the case, you do need to use a weighted average. The median is the halfway point. It just simply divides the data in half. And it's easy to do this if you have an odd number of elements, because you just sort out the data and you find the one that is smack in the middle. If you don't have an even odd number, if you have an even number, then you have to do one more thing. You average out the two in the middle, and whatever that number is, we define that as the median. And you can see in this case, we end up with 2.5. And even though 2.5 is not actually in our sample, it does divide the data into two halves. The important detail is that half the numbers are below 2.5 and half of them are above. Okay, so those are the two cases we might encounter with the median. Now, this is a case where we don't have a formula. It's simply a process that we're following, and it's the same for both populations and samples. Then we discussed this idea of outliers. Of course, an outlier is a value in a sample or population that is either much larger or smaller than all the rest. And the reason why this matters is because if we have outliers in our data, then the mean can be distorted. And in those cases, the median is a better choice as a measure of central tendency. Okay, like here, this case with the students at a SUNY Purchase class, and there's one retiree who's taking this class just for the fun of it. Well, that 75-year-old is certainly an outlier because that person is their age is well above the rest of the class. So if we calculate the mean from this data, we're going to get a very large number, which does not really reflect the average of the class, or certainly not the middle of our data. Instead, in a case like this, we're going to use the median. And we actually did work through this example where obviously this 100 is an outlier. And so we saw that the mean is 19, which is not a very meaningful measure of the center, but the median is 3, which puts it right here. And I think you'll agree that that's a much more meaningful measure of the center than the 19. So the bottom line here is that when we have outliers, we're going to go with the median as our preferred measure of central tendency. If not, we always go with the mean. The mean is easier to understand, it's easier to interpret, and it also has some convenient mathematical properties that the median does not have. So the median really is a special case that's reserved for situations when there are outliers. It's not the case that, you pick the one that you like the best. Pretty much everybody who uses statistics follows the same process. So the median is saved for cases when there are outliers. And then finally, we introduced the mode, another measure of central tendency. This one refers to the most frequently observed value in the sample or population. This one requires us to sort the data and see if any of the values are repeated. There's no formula here, and the results will be the same for a sample or a population. We also saw that for numerical data, the mode is not really the best choice for a measure of central tendency. There could be certain valuable element, some value to this kind of thing, but usually this mode is more useful for cases when the data are non-numerical or qualitative. Here, it's just not quite as useful because, for one thing, there's no guarantee that there will be a mode in the first place if there's no repeated values. And secondly, there can be two or more modes as well. And that makes things a little tricky to analyze when there's two different modes or three different modes. So pretty much we'll reserve the mode for cases when our data is non-numerical. Like we looked at this example of the iPhones and how did they choose these colors? Most likely these colors were the modes of a survey that they did to find out what the public wants to see for these colors. For a case like that, that's a good idea. For numerical data, not so much. Okay. Now, we also introduced the concept of a histogram, which we'll see over and over again throughout the class, which is a way of representing data as a series of bars. And each bar represents either one category or one number. And the heights of the bars represent either frequencies or probabilities, depending on the application. We'll see them again and again. And we saw them here when we're trying to introduce these concepts of data that might be negatively skewed, symmetrical, or positively skewed. You might recall that negatively skewed means mean is less than median, which is less than mode. And we showed a histogram so you can visualize what this looks like. It means that there's an imbalance, the so-called left tail, as it's called, of this distribution. Oops, hold on one second. Once again, I do not have my tablet plugged in and I have to go take care of that. Okay. All right, here we go. So in other words, with a distribution like this long section on the left is sometimes called the left tail of the distribution. It kind of looks like, and this is the right tail. And you can see there's an imbalance between the left and the right tail. The left tail is longer than the right tail. And we call that negatively skewed, where in this example, because it refers to stocks, that means that we have more losses than gains. The next one was symmetry or symmetrical, where there's a balance between the two sides of the distribution. This can only occur if all three of these measures are equal to each other. And so, yes, this is a nice one because you can see there's an exact balance between the left and the right. The gains and the losses match each other. So it's like a big mountaintop. And then we also might have this type of situation, a positively skewed set of data where the mean exceeds the median, which in turn exceeds the mode. Positively skewed looks like this. We have a very long right tail and a relatively short left tail. And in this example, the gains outweigh the losses. So this is ideal from the perspective of the investor. All right, and then we also mentioned that there's many cases where the data don't fall into any one of these categories. Like this histogram shows a case where we don't have any of those cases. It is not negatively skewed, it is not positively skewed, it is not symmetrical. It's just a bunch of random bars, basically. So we often find that many data sets fall into this category. So in other words, it's not necessarily the case that any given data set will be falling into one of these three categories. But when they do, it's important to know that. All right, now, we then introduced the measures of dispersion. This is pretty much as far as we got. I wanted to, with these histograms, illustrate what do we mean by dispersion. The histogram on the left shows a low degree of spread or dispersion because the returns, or actually in this case, they could be any numbers at all. But whatever they are, they're all close to the mean of 10. On the right, we have the opposite case. Many of these are quite far away from the mean of 10. And so therefore, we have a high degree of spread or dispersion. And so what we're trying to do with this measure is capture which is which. And by the way, if you notice, they both have the same mean. So if we're only focused on the mean, that doesn't give us enough information to tell that the distribution on the left is not spread out very much at all, and the one on the right is. So this is potentially very important information. So that's why, in addition to the measures of central tendency, we often calculate measures of dispersion to give us more insights into the data that we're working with. Okay, so if these were stock returns, by the way, the one on the left would represent a very safe investment. So in other words, in the previous diagram, the histogram on the left shows a stock that is very safe. You can see why, because the returns hardly ever move away from that mean of 10. The one on the right, you don't know what you're getting from one year to the next. Your returns could be anywhere from 6 to 14 and anything in between. So therefore, the histogram on the left shows stocks that are safe. The histogram on the right shows a stock that is very risky. And you can tell just by looking at the graphs that this is the case. But ideally, you would like to also have a number that you can associate with each histogram to give us an easier way of comparing them to each other. You know, the graphs are fine, but it's not always easy to see, you know, subtle differences between the two. So that's why we need these measures of dispersion to give us more insights into what's happening with the data. So like here, for example, if we're just looking at numbers, you can see the sample in the top has very little spread because, you know, they're all very close to the center, which is 3, whereas in the bottom, those numbers are quite spread out from each other. So again, we'd like to have a number that we can associate with each sample so we can compare them directly. Now, we're going to introduce 5 measures of dispersion. And they're a little bit messier than what we've been used to, but they're not that bad. And some of them are related to each other anyway. So it's not the case that we're learning 5 completely new concepts here, as you'll see as we go along. So, but these all have their place. And in some cases, one is better than the others. It depends on what we're trying to accomplish. But of all of these, the one you see the most commonly used is the standard deviation, especially in business applications. All right, so we did introduce the range. It is simply the difference between the largest and the smallest element in our sample or population. And like the median and the mode, there's no formula here. We're just taking the data, sorting it out, and then taking the largest minus the smallest. All right, so in this case, the data that we've seen throughout the entire chapter, we sort them out as we've done before, and very simply subtract the smallest, -1, from the largest, which is 5. That means the range is, as you can see, 6. All right, so the spread between the largest and the smallest is 6. You know, and there's so many other ways you can apply this. Like here's another one. What if we have a small class and these are the GPAs of the students in that class? And then for some reason, the school wants to know what the range of GPAs is. What you would do is you take the largest, which is 3.5, subtract the smallest, or 2.2, and that equals 1.3. And that's it. I don't know what you're going to do with that information, but that's the range. All right. So the calculations are the same for samples and populations. So now we're ready for a somewhat more, let's say, complicated measure. The word is called quantiles. And the word quantile actually is a class of measures, which we're going to focus on one of them. There's 3 that we're going to introduce, but we're only really going to focus on one here. Quantiles basically take our data and break it up into equally sized groups. All right, in other words, we could take our data and break it up into fifths or tenths or 20ths or whatever you want to do, but there's certain ones that are more common than others because of their usefulness. Now, percentiles, you're all familiar with percentiles. The data is divided up into 100 equal parts, which represent 1% of the total. So just as a quick example of that, let me just throw that onto the next slide. If you receive a grade on a test, which puts you at the 90th percentile, this means that you did better than 90% of the class and did worse than 10% of the class. Okay, so if you can imagine, maybe I'll draw a little diagram here. Whatever that score is, you did very well. Because that puts you right here. So let's just say that the grade is, I don't know, 92. That means that in this class, 92 represents the top 10% of the class. Now, it's possible that the worst grade in the class is 50. Nobody did worse than 50. It's also possible that nobody got more than a 98. Okay, so this is the number that we have, 92. And so the actual scores are not the important thing here. What matters is that we outperformed 90% of the class and we still did worse than 10%, which is very good, obviously. And if you recall, now you may have taken a standardized test to get into college. For example, the SAT and the ACT exams are standardized tests that you can take in high school. And, they're broken up into different categories. Like I took the SAT and I remember it had three categories: math, verbal, and logic, I think it was. Oh God, it's been a long time. But the point of it is that for each section, let's say the verbal section, the highest score you can get is 800. So what if you get a score of 600? It's hard to be sure how well you did. What does that mean? I got 600 out of 800. Is that good? Is that bad? So they often will tell you, or they usually will tell you, what percentile that represents. So if you were told that that is the 80th percentile, that means you did better than 80% of the other students and you did worse than 20%. So the score may not be as meaningful as the percentile. It's a percentile that lets you know where you stand compared to everybody else. And that's how one of the ways the schools decide who gets in and who doesn't, by the way. Unless something's changed since I was in high school. It's not the only thing. Of course, they look at your GPA and they look at what classes you took and, what activities you were involved with and, your personal essay and all this and that. But this is one of the determinants of who gets into the school. And so it's a percentile that really is the most meaningful number, not the raw score, but the percentile. So these are used all over the place. You also see sometimes deciles, which, it's not a very common thing, but the deciles, the way they work is that instead of hundredths, you have tenths. So in other words, imagine that you were told that your score on some exam is, let's say, I don't know, and that put you in the 8th decile. Well, what that means is that you are somewhere between 80 and 90%. In other words, so this would be the first decile, let's say. This is, let's see, how does that work? This would be the 10th. This would be the 9th. And then this would be the 8. So you're basically at 80%. You did better than 80%, and you did worse than 20%. You know, this, I don't know, you don't see this very often. I think it's easier to just go straight ahead with the percentiles, but sometimes we don't need to be quite that precise. For certain types of applications, it's enough to divide the data into 4 equal parts, which we will call quartiles. And so what we're going to do here is see how exactly do you calculate what quartile a number belongs in. It's a little bit more challenging than what we've been doing, but when we're done, you'll see that it really is closely related to what we've done up to this point. Now, just like with the median, the steps you will follow depends on whether you have an even or an odd number of observations. All right, yes, there's no getting around that. That matters. It will help us determine the quartiles. You have to first determine whether you've got an odd or an even number of values. So in the odd case, we take the data and then we sort it out from low to high. So you can see there's 7 values. Now, it turns out, here's an interesting result. All right, so on the next slide, I'm going to show you the same data where I'm going to highlight a single number. And if you notice that single number is 14, it is in the middle. We already know that this is the median, but because of the way the quartiles are defined, the first quartile, which we'll from now on call Q1, is the range between 0 and 25%. The second actually represents the next 25%, but when you look at a plot, hold on one second, let me finish this. There is, by the way, there's no 4th quartile because that would represent just the highest value. So in other words, you have to visualize that. Here's the data. Actually, that doesn't have to be 0. This would be the smallest value in your data set. Let me write minimum here. This would be the first quartile. This would be the second. This is the third. And this is the maximum. So the first quartile is the bottom 25%. The second is the bottom 50%. The third quartile, bottom 75%. There's no 4th quartile because it would simply be the largest value. It covers all 100%. So these are the 3 that we'll be calculating, but because of the way this is defined, the median is the second quartile. Okay, it's the same thing. So that one is easy to calculate because we already know how to do that. The question is what to do about the first and the third quartiles. Well, it turns out that's easy too, because what you're basically going to do is take your data and split it up. And within each of these 2 halves of data, the first quartile is the median of this lower group. And the third quartile is the median of this upper group. Okay, so in other words, you're calculating essentially 3 medians here, the median of the entire data set. Then we split the data up into the lower group and the upper group. And then within each group, we find another median. So basically, these quartiles are medians of different groups of data. So you're essentially applying the median concept multiple times here. All right, so does that make sense? Good. Now, you might think, what an odd concept. So I've actually taken standardized exams where the results were reported in quartiles. There's one that I took that involves risk management as a profession. And if you take this exam, it makes it easier to get into that field. And all the results were in quartiles. And they would say, well, listen, your score in the quantitative section of the test was, let's say, the third quartile. And, or something like that. And that way you don't have that precise information about how you did, but at least you know where you stand more or less compared to everyone else. So yeah, it has its place. When you don't need such specific information as percentiles, but you still need to have some idea of where you stand within a sample or a population. Now, again, what about the even case? We sort the data from low to high, and as you know, in order to calculate the median, what you're going to have to do is find the 2 in the middle. So let's do that right now. So this is the same data, except, whoops, I bolded the 2 in the middle for you. And the median, as we know, is 3.5. That's both the median and the second quartile. Then we're going to do the same thing, except now we've got our 2 data sets. The lower and the upper are these 2 groups. And we once again have an even number of values. So what do? Well, we're going to have to apply the same technique we just saw yesterday. The average of these 2 is the first quartile. The average of these 2 is the third quartile. So once again, we've applied the median concept 3 times, once for the entire data set, and then once each to the lower half of the data and the upper half of the data. So again, it is basically a simple extension of the median. It's not something completely new. All right, now here's where this actually does come in handy. It seems, like, well, I don't know if I can think of any real good examples of when this comes up, but here's one. It turns out that what this enables us to do is figure out what values belong in the middle. And literally the middle means the middle 50%. So, for example, imagine an exam. And let's say the scores are, the worst score is 40, then we have 52, 77, and 90. What we are interested in sometimes, oh, actually, no, sorry, let me make this 100. We might be interested in knowing middle 50%. And in this case, that would be everything from 52 up to 90. If you got in that range, then you're in the middle of the pack, basically. If you fell below that, then you did very poorly. This is the bottom 25%. But if you finished above that, you're in the top 25%. For some applications, it's the middle that we're interested in. So we have this concept, which is called the interquartile range. And it's very simply defined as the difference between the first and the third quartile. So for this case that I created up here, that would be 90 minus 52. $38. That's the range of scores in the middle 50%. I was just going to make a note here. So you'll be wondering later on what this is all about here. Now, what does this have to do with what we were doing yesterday? Aha. I did mention yesterday that there is an official formula for identifying outliers. Well, here it is. It turns out that it's defined in terms of quartiles and this interquartile range. So within our data set, an outlier is any value which is either greater than the sum of the third quartile plus 1.5 times this IQR, or less than the first quartile minus 1.5 times the interquartile range. This way, we don't have to rely on our judgment or our opinion. We know that there's a specific definition which identifies whether a value is an outlier or not. That's kind of nice. I mean, you don't want to be getting involved with opinions because everybody may disagree about whether something is an outlier or not. We want to have a precise definition that we can all agree on. And so this is that definition for outliers. Now, in fact, if you want to, you know what we could do here? Why don't we do this? Let's go back and grab this example. And let's find out what numbers would qualify as outliers, just so you can see how this works. So these are the original numbers. And we determined that Q1 is 1.5. Q2 is 3.5. And Q3 is 5.5. Okay. What we're going to do now is identify what it would take for a number to be an outlier. All right, so we'll start with this one. And that's going to be 5.5 plus 1.5 times, oh, and we also determined that the interquartile range we did not, because we just introduced this idea. 5.5 minus 1.5 is 4. Okay, great. So that means 5.5 plus 6 is 11.5. So if we included in our sample a number which is greater than 11.5, it would be considered an outlier. Now, on the lower end, we have this definition. So we're going to find out right now what would qualify as an outlier. All right, so the first quartile was 1.5. Okay, minus 4.5, any number less than negative 4.5 is an outlier. And that's, of course, for this sample, only for this sample. All right. So now we know how to figure out what is and is not an outlier. Now, the examples we use in some cases were quite a bit exaggerated, just to make sure you can see what it's all about. But if you look at these numbers carefully, you see they're really not that far above or below what we have already. So, in some cases, outliers are surprisingly small. The key is that how far away are they from the rest of the data, not how large or small are they in absolute terms. All right, now, of all the measures of dispersion, the next one, in my opinion, is the most challenging to calculate. And in fact, you'll see why yesterday we spent so much time really studying the summation operator. And in fact, I think I mentioned it that this one case, the scary case, is going to come in handy today. And now that moment has arrived because we're about to see why this is useful. We're going to need this to calculate the variance of a sample or a population. So we'll start with the sample variance. And this time, once we actually have a formula again, it's been a while since we had a formula, hasn't it? Yes, too long. We were dying for a new formula. So let's see it. And you'll say, hey, it looks a lot like that. And that's true. This is the formula for a sample variance. Now, the thing that I want to point out is that we are subtracting a constant from each term in our sample. The constant happens to be the sample mean, which of course is a constant. It's a single number that never changes. So therefore, we are indeed subtracting a constant from each of these elements. And then we, once again, like yesterday, we subtract, we square, we add them up. And now here we're dividing by the sample size minus 1. And the notation we use for the sample variance is S squared. Remember, yesterday we said that sample measures are described by, oops, Roman letters. And that's what we see here. The square is because of the way this is calculated. That's why we use that symbol. So yeah, now something like this, it's not really that difficult, but you have to be really careful. That's the problem here because it's so easy to make mistakes with it. All right, so let's take a look at an example. Now, actually, this is the same sample we've been seeing throughout the entire chapter. Let's see. These numbers, yes, you're very familiar with them already. Now, if you look at this formula again, I'll tell you what, let me just copy it down here. You'll notice that before we do anything else, we need to know the value of X bar. So that has to come first. But of course, we know how to do that. And in fact, you may even remember, because we've already done it, that the sample mean is 2. All right, but let's go through it again and prove it. And so, yes, we take all the amounts. And by the way, if you notice, in this case, the data do not have to be normal. Normal. Have to be sorted. You can, but it's not necessary. So you see here, we're leaving the data in the original order because it doesn't affect the results. So as we remembered, the sample mean is 2. All right, now for the next page or slide, I'm going to copy these numbers so you can see them again. All right, now why did I put those there? I want you to see that this number is X1. This is X2. This is X3, X4, and finally we have X5. So all I did was go through each of those 5 elements. I'm subtracting the mean, which we already have determined is 2. Then I'm going to subtract, square, and divide not by 5, but by 4. It's n minus 1. So what you might want to do is do this in 2 steps. First, calculate the differences before you attempt the squares. Because I find that when you try to combine 2 steps at a time, that's when you start to run into trouble. Okay, so again, the whole idea here is you've got to be careful. One little mistake and the whole thing is wrong. Okay, now you can square them and add them up. And finally, at the end, divide by 4. And you can see, I'll give you a minute to catch up. Okay. All right, so on the next slide, you can see that that comes down to 0 plus 9 plus 1 plus 9 plus 1 over 4, which is 24ths or 5. So that is my variance. So that nightmare is over. But like I was saying, this is definitely the worst calculation in this section of the, at least for the measures of dispersion. You can do that one. You're already moving ahead pretty fast. But anyway, I do want to mention here that, as is the case in with so many statistical measures, most of these measures have good points and they have bad points. That's why it's important to have so many different ones to choose from, because depending on what kind of data you have or what you're trying to analyze, some of the measures might be more appropriate than the others. Now, here's a case where we have a real problem. Here's what's going on. So suppose that the data used for the last example represented degrees Celsius. Okay, so in other words, we never mention what these numbers are supposed to be. Imagine these are temperatures in Celsius in the month of December. And the problem here is that because of the way variance is calculated, it is measured in squared units. What does that mean? So in this case, the variance is actually 5 degrees squared. Now, what in the world does that mean? Does anyone know what a squared degree is? No, there is no such thing. So that's pretty awkward. So what do we do about it? Good question. This is clearly to interpret so we can make an adjustment by creating a new measure called standard deviation, which avoids this problem. So in other words, the next measure of dispersion we're about to look at, which is called the standard deviation, the reason why it exists is to avoid this problem with the squared unit. And so all we do here is very simply, we take the square root of the variance. Okay, in other words, that, and by the way, that will get rid of the problem. This eliminates the problem of squared units. So based on our last example, look how easy this is. It's just, look, you just took the square root of the variance. In fact, you could write it as S equals the square root of S squared. And that's all there is to it. So when you do the variance, you're also, in effect, doing the standard deviation. You're almost getting two measures for the price of one. So based on the last example, we're basically then going to determine the standard deviation to be the square root of 5. And that's all we have to do, which is about 2.236. So this, if our data is measured in terms of degrees Celsius, then the standard deviation is 2.236 degrees. Okay, so there you go, problem solved. And for that reason, the standard deviation is much more widely used as a measure of dispersion than the variance. Now, the thing is, you'll probably say to yourself, now, why do we bother with the variance? Well, because we have to calculate the variance to get to the standard deviation. So you can't ignore the variance. So, but what it does mean is because of the units problem, when we calculate our variance, we then take the next step and we take the square root and come up with our standard deviation. Okay, and just as an application, and this is if you're interested. If you're not, you know, that's okay. In the financial markets, the standard deviation of the returns to a stock is the most commonly used measure of risk. Okay, this standard deviation is often referred to as the stock's volatility. You might have heard that word. If you watch like CNBC or something and they talk about volatility, they're talking about how much the stock's returns are bouncing around in the market, which is normally measured by the standard deviation. Okay, so if you're, you know, studying business of any kind or economics or finance in particular, this is good to know. As a matter of fact, if you're in any of those fields, statistics is going to prove to be maybe one of the most important courses you can take, because everything in economics and finance is based on statistics. Or if you're studying psychology, same thing. All the research is done based on statistics. So it shows up everywhere. Okay. All right. Anyway, now for the population version of this formula, it turns out this was the first time that the formula will be mathematically different than the sample version. Okay, so let me show it to you. Now, this is it. By the way, before we do that, let me go back and get the sample version so you can compare them side by side. Because I want you to see something important. Not only is the notation different, you know, the Greek letters and all the rest, but there's a very important mathematical difference. For starters, here's a paradox. Our old friend, the summation operator, is the Greek letter sigma, but guess what? So is this one. How did that happen? Did somebody goof? No, because like the Roman alphabet, the Greek alphabet has case. The summation operator is the uppercase sigma. This symbol is the lowercase sigma. All right, so it's not a paradox at all. And so sigma squared is the population variance. And we already knew that capital N is the population size. To distinguish it from lowercase n, which is the sample size. And of course, you notice here, we've got mu, which is the population mean. It replaces x bar, which is the sample mean. But here's what I wanted to draw your attention to. Look at the denominator. They're not the same, are they? Now, it's a very subtle distinction. And the reasons for this are crazy technical, so we won't get into them here, but this is the first time, like I said before, that the difference between the two measures is not just the notation, but the actual calculation itself. So when you're doing a problem, it's very important to note at the beginning whether you're dealing with a sample or a population, because it will affect this formula. Most of the other measures, it doesn't really matter, but this one it does. So in order to avoid getting this wrong, make sure you're aware when you do a problem, whether you're dealing with a sample or a population. Okay. Now, we're not going to need to do a completely separate example for this, but I do want to show you that just like with the sample case, the standard deviation for a population is also nothing but the square root of the variance. Okay, so let me show you that on the next slide. Because again, the same issue arises where you have squared units, whether it's a sample or a population. All right, here we go. There we are. It's nothing but the square root of the variance. And in fact, this will always be true no matter what type of data we're working with. The standard deviation is always the square root of the variance. All right, now there's one more measure that we want to look at in this group. It's called the coefficient of variation, and it's actually an interesting measure because it's simply a mixture of two other measures that we already know. We'll see why this is important in a second. So we now are introducing something called the coefficient of variation, and it basically combines both a measure of dispersion and a measure of central tendency. So it's like a hybrid measure, or sometimes it's known as a measure of relative risk. Or I guess what we could do in general terms is called a measure of relative dispersion. And when we say relative, we mean relative to the mean. In other words, we're trying to get a sense of how big the dispersion is compared to the mean. And this is very, very helpful when analyzing investments in particular. Well, here's the general formula. It applies to both for populations and standard samples. You're going to take your standard deviation, divide by the mean, you're going to multiply by 100 to turn it into a percentage, and you're done. So the sample version would therefore be and the population would therefore be this. Okay. Let me just clean that up a little. All right, so let's do an example. So we got two portfolios of stocks, and we're going to assume that we'll treat these as populations. It doesn't really matter if they're populations or samples. The focus is on the rates of returns, and we're trying to compare the two. Now, for portfolio A, the mean return is 8% per year. The standard deviation is the risk. Now, by the way, if you notice, with returns to stocks, these are both percentages. 8% is the return on average, but 16% measures how much uncertainty there is from one year to the next. In fact, you know what? Let me do this real fast. Let me draw a little picture here. Imagine you have a stock. And let's see if we can show how its price evolves over time. All right, this stock grows very slowly, so it's going to have a very low standard deviation because it doesn't change very much over time. But then imagine this stock. Whoa, that's a very different ball game, isn't it? Now, the one on the left is very boring, but it's safe. The one on the right, look at that. It goes to these huge ups and downs. It's going to give you an ulcer eventually if you own this thing. So I just want to give you a feel for what standard deviation is trying to capture. You know, it's essentially telling us how much it bounces around over time. The higher the standard deviation, the riskier the stock is considered to be. But normally, and let me just mention this as well, because you're probably wondering, well, then let's all buy the low standard deviation stock. But the reality is this. In an efficient financial market, the stocks with the highest risk tend to have the highest average returns as well. So in other words, you got to take the good with the bad when you buy these stocks. If you're going to buy the stock on the left, the boring stock, you don't have much risk there, but you also don't have a lot of upside potential for your returns. If you buy the one on the right, you're going to be very worried about it all the time, but the potential for high returns is quite good. So in other words, the one on the left was great if you're a very nervous person about your investments. You don't want to take too much risk. The one on the right is great for people who love to gamble and they're willing to roll the dice a little and buy a risky stock with the potential for higher gains. Now, what we're trying to do is essentially combine the risk and the return into a single measure. And that's really what this coefficient of variation is doing for us. So with population B or portfolio B, the return on average is 10%, but the standard deviation is 30. Okay, so again, this is the return or mean return. And this is the risk as measured by the standard deviation, which once again reflects the uncertainty over the price in the future. Now we're going to calculate the two coefficients of variation and compare them side by side. For A, if you recall, the mean was 8, the standard deviation was 16. So that gives us a ratio of 200%. For B, let me just give a minute to catch up. We have a ratio of 30% to 10, and that gives us a ratio of 300%. So because B is higher than A, that means the amount of risk that we're taking on compared to the return is higher than for A. In other words, the risk is 3 times the return. Here, it's only 2 times. So even if you're a gambler, you might look at this and say, maybe I should stick with A because the amount of risk is only double the return, whereas here it's triple, and that's a very high number. And this is one way you can compare the performances of the 2 stocks. You can say to yourself, well, I'm not sure. This is a very risky stock relative to its return or portfolio. So this gives us more information than just looking at the mean or the standard deviation by themselves. And that's why this is so important. All right, so we're actually done now with the measures of dispersion, and that just leaves us with the third and final set of measures. And this one is different because now we're looking at the relationship between either 2 samples or 2 populations. These are collectively known as measures of association. So I'll explain, I hope intuitively in a minute, what this actually means, but note that there are 2 different measures that we can use here. The first one is called the covariance, which is very close to the word variance. And you'll see why when we do the calculations. And then correlation, which you've probably heard of before, without maybe necessarily understanding what it means. And just like before, these 2 measures have pros and cons, I guess. And so let me just try to explain to you what exactly association means. Just as an example, the sales of a corporation and the profits of a corporation tend to rise, be closely related to each other. In other words, when sales increase, profits usually increase. When sales decrease, profits usually decrease. So we would say that these 2 variables are closely associated with each other. And so what we would like to be able to do is come up with a sense of how close are they. We'd like to come up with a number that reflects how closely these 2 variables tend to follow each other. Now, this is the kind of thing we can illustrate with a graph. In fact, I think, I'll go take a look and see if I can find a quick graph that I've hopefully already put together. Here we go. If I didn't post this, I'll put it up there when we're done. What I've done is made up an example for you. And so here's sales for this corporation over the last 10 years, and here are the profits. And what I did was I went to Excel and I produced this special type of graph, which is called a scatter plot. And as you can see, I hand wrote the rest of it myself, but the points, each point represents a single year in my sample. So this one is year 3, for example, this point I'm pointing to right now. This one is year 10. Let's see, let me find another one here. It's being stubborn with me, but anyway, this line through the points is called a trend line, and it's an attempt to capture the relationship between X and Y, which, by the way, I almost forgot to point out. On a plot like this, you'll notice on the vertical axis I have profits, and on the horizontal axis I have sales. That's because we're assuming that profits depend on sales. It's not the other way around. And so the profits are referred to as the dependent variable or the Y variable, and the sales are the independent variable or the X variable. In fact, let me just throw this in here. I can't do that because it'll mess up my graph. Oh, too late. It's already kind of a mess now. Yeah, what I was trying to do here, I guess. This is supposed to be what you're seeing, those lines there are supposed to represent the XY coordinate system. And you might recall with the XY coordinate system, we have 4 quadrants: the first, the second, the third, and the fourth. And what separates them all out is in the first quadrant, both X and Y are positive. In the second quadrant, X is negative and Y is positive. In the third quadrant, X is negative and Y is negative. And in the fourth quadrant, X is positive again, Y is negative. So if you notice with these points, they all tend to be in the first or the third quadrant. Both variables are either positive or negative most of the time, which means that they follow each other very closely. Okay, so oh yeah, I wanted to add one more thing here. Sales are the independent X variable. Profits are the dependent or Y variable. And that's why they're listed this way. So in this case, it's pretty clear that these two variables are very closely related to each other in the sense that when they're both positive, they're either both positive or both negative most of the time, if not all the time. So down here, I've changed the variables to costs of production and profits. Now, obviously, as costs of production go up, profits tend to go down for the corporation. So these variables go in opposite directions. And you can see that this trend line is negatively sloped and that most of the points are either in the second or the fourth quadrant, where X and Y have opposite signs. So we conclude here that these two variables tend to go in opposite directions, or sometimes we say they are negatively related. But you can see that by looking at the scatter plot. What the measures, covariance and correlation, will do will enable us to quantify that. And then there's a third example here, a silly example, really, where I'm comparing temperature with profits. And, you know, let's face it, there's no reason why the temperature should have any influence on our profits. So here, the two variables, the points are randomly scattered around. They end up in all 4 quadrants. The trend line is flat. And that's because these variables are not really related to each other at all. So these are the 3 basic cases: positively related variables, negatively related, and unrelated variables. And so the covariance and the correlation will help us understand what kind of relationship there exists between 2 variables, if any. Okay. So that was our little detour. And what I'm going to do, before I forget, let's see if Moodle's still open here. I did not post it, but I'm going to do that right now because I want you to be able to see what just happened there. just so you can conceptually understand what these two concepts are all about. Yeah, we don't want to lose this. All right, so what remains now is to see how these formulas work. Now, unfortunately, these formulas are fairly complicated. So we're going to start it right now, but we may have to finish this tomorrow. And by the way, once this is done, the chapter will be done and you'll be able to do the chapter 3 problem set for next week. And then we can dive into 5, which is a very different chapter than 3. 3 is more computationally oriented. Chapter 5 is a little bit more conceptual. It'll be interesting to see which one you like better. But anyway, let's get back to this for a second. Now, covariance, let's jump ahead here, has a formula for samples and for populations. This is the scary formula. Now, you notice there's X's and Y's involved here because we're going to have 2 different samples. One will be the X's and one will be the Y's. So you can probably guess that this is a single element in sample Y, and this is the mean of sample Y. N is this common sample size of the 2 samples. They have to have the same number of elements. And this, of course, we don't have to repeat it, but it's an element in sample X. And this is, of course, our old friend, this mean of sample X, X bar. So there's really nothing completely new here, except for the idea that we have 2 different samples going on. Also, if you notice, we're using S again. To avoid confusion, we have these 2 subscripts. So don't confuse them. S is the sample standard deviation, which means for a single sample, whereas SXY is this sample covariance. So rather than coming up with a new symbol, somebody decided to have subscripts. All right, so now, now here's the sample that we're going to look at. 2 sets of data. So the first thing we have to do is calculate X bar and Y bar. All right, so let me just quickly show you, since we're running out of time here. Remember, we have to stop at 11:30 today, unfortunately, because I have to drive a very long way to give an exam at another school. But this is the last time, okay? I don't want to cheat you out of any statistics, that's for sure. X bar, as you know, means we simply add up all the elements, divide by the size of 5. So X bar turned out to be 1. And of course, we know how to do this. This is not a problem. We're now experts in calculating sample means. Imagine that, after one day, we're already experts in sample means. And then for the Y's, same thing, except this time it's 15 over 5, which is 3. Okay. And if you look at the formula, by the way, you notice it's set up exactly the same way as this one. Except we replace the X's with Y's. That's literally the only difference. Okay, so let me just copy this one more time. And that's the starting point. So we got 1 and 3. which we'll need to use very intensively in this formula. Now, the formula, let me just go grab that formula again so you can see what we're going to do. Okay, so if you look through, now this looks very scary, but what we've actually got here is x1 minus x bar, y1 minus y bar. Then we follow that up with x2 minus x bar, and then we have y2 minus y bar. Okay, so you can see the pattern that's emerging here. Then here we have x3 minus x bar, y3 minus y bar, x4 minus x bar, y4 minus y bar. And then finally we have x5 minus x bar. And then when we do the calculations, oh boy. There we go. And you notice we divide by n minus 1 like we did with the sample variance. Oh man, what happened here? They're all off. Okay. Oh, these are off too. Hold on. Okay, now we're all lined up. Okay, we're good. And so you can see for yourselves at the end, we ended up with -1. And the sign is going to tell us that the two variables are moving in somewhat different directions, but it's hard to tell for sure what they're going to look like without a graph. Okay. So yeah, this is, you can see this is really probably the messiest form that we're going to see maybe throughout the entire semester. I don't know, but make sure that what you're doing is you're always doing them at the same. In other words, x1 goes with y1, x2, y2, all the way through the entire list of calculations. Make sure they're lined up properly. And of course, in each case, you're subtracting the corresponding mean. And when you're finally done at the end, you'll end up with your result, which, and this is one of the challenges with covariance, it isn't necessarily easy to interpret what that means. All right, so I think we're getting into some very deep waters here that we don't want to rush through. So, you know, maybe we could stop right here and then we'll come back and revisit this tomorrow. We'll go through it again from start to finish to make sure we really get it. And then we'll introduce the other version of this, or the other measure of association, which is correlation, which will prove to be the more important of the two. And then we'll be done with chapter 3. So we can move on to something a little bit more conceptual and not so computational. But anyway, we're doing well here, I think. Just make sure you're keeping up with all of this. Make sure you can reproduce these results with your calculator. And if you can, and also you might want to start looking at the problem set, even though we're not completely done here, you should be able to do most of it by now. And so we'll pick it up tomorrow. And our usual time. And what we'll do is we'll finish this chapter and then we'll dive into 5 and see how far we can get. Then we'll be off for Christmas. Woohoo. And then when we come back, we'll just continue with what we've been doing. And so I guess unless there's any questions, oh, here's a chat. Sorry, I didn't see this. Oh, yeah, try to have it ready by Monday. I think that's the best. Although this weekend is Christmas, isn't it? I'll tell you what, if you're not ready until Tuesday, that's okay. How about that? Why don't we decide that this week only, Tuesday will be the day for the exam. Problem set, just because it's Christmas over the weekend. And yeah, I think that's fine. I don't see any reason why you should have to worry about this during the Christmas weekend. But, so if you do it on Monday, that's fine, and hand it in by Tuesday. All right, anything else? All right, well then, I will see you all tomorrow then, at our same time, same place. You're welcome, everyone.
Thank you.
Okay, bye.
Bye.
Bye.